Okay, welcome to our concepts video for section 1.2, where we're going to be talking about evaluating limits algebraically. Well, what does that mean? That really just means we're going to try and evaluate limits without having to rely on a graph. Because that's mostly how we looked at it yesterday. In our last video. That's mostly how we looked at it in our last video. So, if I want to evaluate a limit without a graph, how do I do that? Well, let's start by taking a look at a relatively simple example. Let's say I wanted to know the limit of x squared plus 5x as x approaches 0. Well, x squared plus 5x is a continuous function. It's a polynomial, and polynomials are continuous everywhere. We noticed in our last video, in section 1.1, that if my function is continuous, all I need to do is just plug in the x value. And so this limit just ends up equaling the value that I get when I actually just plug in 0, which in our case is just 0. Well, this is because continuous functions have some important properties when we're talking about it in terms of limits. So this is what's called the limit definition of continuity. This is what it means for a function to be continuous when I'm talking about limits. Okay? A function f of x is continuous at a point x equals a if the following three criteria are true. Criteria 1. Well, first of all, f of a has to exist. If the function value has to actually exist. If I plug in the value into my function, I should be able to get some sort of output. 2. Well, we saw yesterday that if the limit, you can approach a limit from two different directions. What happens if your limit goes to two different values at different directions? If I approach two different values from my different directions, I end up with a jump discontinuity. So I end up with a function that's not continuous at a point. So in order for my function to be continuous, the limits from either direction have to be the same. And this is condition 2, that my limit from the negative side and the limit from the positive side has to equal the same thing. Well, if those two limits are equal, that means that the limit in general exists, right? That means that this limit, if I don't specify a direction, that this limit will exist because the limits from either side will equal the same thing. Well, the last condition is that whatever this limit is, it has to equal whatever the function value is. If that's not true, then we might end up with something like, I should have kept that as black. Well, if that's not true, we might end up with something like this, where, you've got your function, and from both sides, it's approaching the same thing, but it doesn't match what the function value is. Remember, we call this a removable discontinuity. So that third criteria has to be true in order for it to not be a removable discontinuity. So those are my three criteria for a function to be continuous. And as long as a function is continuous, we know that all three of those things will be true. So, if a function is continuous at a, then this is kind of the important conclusion we can get from this. Then the limit as x approaches a of f of x is just equal to the function value, right? You can just plug in that x value. You can plug in whatever x is approaching to get your function value, and then you have your answer. But what if it's not? Consider this function, where if I tried to plug in my x value of 0, what do I get? I get 1 over 0, which is undefined. So how am I supposed to figure out this limit if I don't have a graph? Well, it turns out that this result also tells me something. it doesn't give me the answer quite yet, but it does tell me something. This tells me that my numerator is staying constant, or at least my numerator is approaching some positive value. In our case, positive 1. So my numerator is approaching some constant value of 1. But my denominator is approaching 0. Well, what happens to your fraction if your denominator gets infinitely small, right? What happens to my numbers if my denominators get smaller and smaller? What's happening to my fractions? Well, this fraction is equal to 10. This fraction is equal to 100. This fraction is equal to 1,000. So as I make my denominator smaller, even though my numerator is staying the same, if my denominator is getting closer to 0, this value is approaching infinity. And I'm actually going to say an infinite value because it could be approaching negative infinity depending on your function. But if you ever get this result where you have a constant divided by 0, that tells you that your function's approaching an infinite value. Or another way we can think about it, remember, that's a type of discontinuity. So I could say it's approaching an infinite discontinuity. So I don't need a graph to tell me that. Just getting this result of 1 over 0 or any constant over 0 means I'm approaching an infinite discontinuity. So let's summarize that. If you try plugging your x value into your function and it results in a constant, so C is for constant, over 0, so that's your result, right? Of course this value is undefined, but this tells me something. Then the function has an infinite discontinuity at x equals a. Well, let's look at another quick example. Well, hopefully you guys are starting to pick up on a good way to start all of these problems. If I give you a limit and I want you to evaluate it without a graph, a great way to start is just plug in the x value. Because what have we learned? We've learned that if the function's continuous, then I should get a value out, and then that's my limit. My limit is just going to equal whatever the function value is. If my function's not continuous, but I get a result like this, of C over 0, then I know I'm approaching an infinite discontinuity. So let's try it with this one. If I just plug in 5, I get 5 squared minus 25 over 5 minus 5, which is equal to 0 over 0. Well, what does this tell me? This actually tells me nothing. Let me rephrase that. This is called an indeterminate form. 0 over 0 is what's called an indeterminate form because if you get this result, it doesn't tell you anything useful besides I need to do some more in order to figure this out. I need to manipulate this formula a little bit more until I get a more concrete result. So what does this tell me? This tells me I need to keep going. So from here, we have lots of different algebraic tools that we can use to try and simplify this expression. Take a look at x squared minus 25. Any ideas of how I can simplify this? Well, it turns out the numerator is factorable. I can factor that numerator and I get x minus 5 times x plus 5. And notice once I do that, this x minus 5 factor on the top cancels with the x minus 5 factor on the bottom, which leaves me with this. This limit as x approaches 5 of just x plus 5. Now, x plus 5 is a linear function that's continuous everywhere, which means to evaluate this limit, since I've removed the denominator factor that was causing my 0, right? X minus 5 is what was getting me my 0 factor. Since I was able to remove it, I can now go ahead and just plug in 5, and I get 5 plus 5 equals 10. And that's my answer. So, by doing a little algebraic manipulation, in this case factoring, I was able to reach a point where I could plug in the number and get a defined value. And that's my limit. I didn't need a graph. I was able to do it algebraically. So we're going to see a few different examples. You'll see a few different examples on your homework where you just have to use different tools. Factoring is one of our tools. Let's look at an example like this, where you have the square root of x minus 9 over x minus 81, and your limit is as x approaches 81. What tool can I use in this situation? I can't really factor this, but I can multiply by the conjugate, if you remember that. Anytime you see a square root, this is an option for us. Just remember that if you multiply the top by a factor, you also have to multiply the bottom by the same factor. Okay, so that's another tool I have. Conjugates. I can multiply by a conjugate. Okay. What about this example? What could I do to maybe simplify this? Well, I can combine the fractions. I have two fractions that are being subtracted in the numerator, and I can combine those just by finding a common denominator. So in this case, I would get 3 over 3x minus x over 3x, right? I multiply the first fraction by 3 over 3 and the second fraction by x over x. I can also combine fractions. That's another tool I can use. Okay, so these three different algebraic tools can help us evaluate limits that otherwise would just give us that. If I don't do that, I'm just going to get 0 over 0 again. I'm getting that indeterminate form. These are tools that we can use to evaluate these different limits that would otherwise give us 0 over 0. Thinking about it now, just to kind of finish this conjugation one, or at least get us a little bit farther, what happens when you multiply a factor by its conjugate? Square root of x times square root of x gives you just x. Square root of x times positive 9 gives you 9 square root of x, but then negative 9 times square root of x gives you negative 9 root x. So those terms will add to equal 0, right? You get plus 9 root x minus 9 root x. So your middle terms go away. That's why we like conjugates, is because it gets rid of your middle terms, which in our case are square roots. And then your last term is just negative 9 times positive 9, which is negative 81. And hopefully you can see how that helps us, because now we have an x minus 81 term in the numerator and an x minus 81 term in the denominator. And once again, that is using conjugates. Perfect. So we can use those tools in order to evaluate limits that give us that 0 over 0 factor. And that's our concept for today, is these are the different ways that we can evaluate limits even without actually having a graph. So that's all I wanted to talk about for this concept video. Go ahead and try the homework out. And if you have any questions, I'll be going through a couple of the problems from the homework in my examples video. Thanks, guys.